Here is the lecture for section 4.5. Remember, the theme of this chapter is how we can use derivatives. One of the things that we've seen many times earlier is that we use derivatives to find the equation of tangent lines. This section talks about maybe formalizing that a little bit, calling that action of finding a tangent line linearization. And let's talk about why that's important. Let's imagine this very, very crazy function here. Crazy function. But what if we find the tangent line of this equation at this point? Well, we know we need a point. We have half a point. The point is, well, actually, we're given the point of 1, 0. We're going to need a slope. And we find the slope by taking the derivative of that function. Let's bring the power down, keep the inside the same. 3 zeros. Reduce the power by 1, -3/4. And don't forget the chain rule, 2x. We're going to try to find the slope at 0, 1. So how about we put in 0 for x, we get 1/4 times 0 squared plus 0.0001 to the -3/4 power times 2 times 0. Well, that ends up just being 0. So we're going to say that the tangent line, and normally we would say, and the tangent line is y equals y value plus slope times x minus the x value. Well, that ends up just being y equals 1. So this very complicated function has a very simple tangent line. Now, why is that important? Well, let's go to the calculator. Let's take a look at what these two functions look like side by side. Remember, the first function was x squared plus 0.0001 to the power of 1/4, and then at the end of it was 0.9. Gosh, that function almost looks like it doesn't have a derivative. Let's put in the second function. That was just simply y equals 1. And you're like, what does this show us? Well, what we're supposed to get out of this little demonstration is that while these don't look like the same graphs, if I do something like zooming in again and again and again, eventually what we see is that tangent line and the original function look pretty similar, at least for a little while. And the more I zoom in, the more you can see how much longer it can be that it's close. Now, we're zoomed in quite a bit. So we might say something, yeah, the tangent line is a good approximation of the original function, at least for some small regions around the point of tangency. It represents a reasonable approximation if the function is differentiable, at least around some small region around the point of tangency. And we're going to call that tangent line the linearization of that function at that location. In this case, we'll use the function letter L. L is equal to 1. L is an approximation of f at least around x equals 0. All right. So why would we want to do this? Well, in an era when we didn't have great calculators, we might use these linearizations to make good approximations. So, for example, how good is this approximation? I've got this function, square root of x of 1 plus x. We're going to find its tangent line at 0, and then we'll use it to make an approximation. So if f of x is, and I'm going to rewrite this as 1 plus x to the 1/2 power, f of 0, and purposely choose 0 here so that we see that the calculations for that tangent line are relatively easy. That's the square root of 1, which is 1. Let's take the derivative of that function, bring the power down, leave the inside the same, reduce the power by 1, which means we've got 1 over 2 times the square root of 1 plus x. What is f prime at 0? It's 1 over 2 square root 1 plus 0. That's 1/2. So we might say the linearization, this function is estimated by the linearization point, and that is 1 plus slope 1/2 x minus 0. All right, great. So what is the value of f of 1.02, the square root of 102? Oh, I'm sorry. That's going to be, yeah. No, this is going to be f of 1.12, right? F of 0.02 is equivalent to the square root of 1 plus 0.02, which is the square root of 102. Okay, so we know that's true. But f of 0.02 is approximately the linearization at 0.02. Go back to that definition of our linearization, 1 plus 1/2 times 0.02, which is 1 plus 0.01 or 101. Is that a good approximation? Well, let's compare the two. Let me add a calculator page. I will say square root of 102. That's the real value of the function. I'll do Control Enter so we get a decimal representation. And what was our comparison? 1.01. How close is 1.01 to 1.00995? It's really, really close. It's really close. So this gives a really good approximation. And please note that, of course, at 0.02, we are relatively close to the point of tangency x equals 0. Let's try this again, maybe with cosine. Again, we're going to try to estimate this. We'll use f of cosine. F of x is cosine of x. Our point of tangency is at x equals pi over 2. So f of pi over 2 is cosine of pi over 2, which I think is 0. Let's find the derivative. Derivative of cosine is negative sine. So the derivative at pi over 2 is negative sine of pi over 2. And I think sine of pi over 2 is 1, so this ends up being negative 1. So our function can be approximated by the linearization, and our y value is 0, minus 1 our slope, x minus pi over 2. Great. So cosine of 1.75, which is equivalent to this function, its value at 1.75, can be approximated by saying it's negative 1.75 minus pi over 2. And let's see how close we get. Cosine of 1.75 is that. And what did we say? 1.75 minus pi over 2. Okay, one's positive, one's negative. Oh, I'm sorry. The linearization was all of that, but there was a -1 out in front. There we go. So how close are they? Well, they're correct to two decimal places and within 1/1000th of a third decimal place. Pretty good approximation for not a lot of work. Great. Let's do 2 more of these examples. Let's use tangent line linearizations to estimate the value of 100, the square root of 123. Now, they haven't told us a function. They haven't told us a where, right? And I don't know the square root of 123 off the top of my head, but let's say for this first example, let's say f of x is the square root function. And I'm going to use a value for x where I know the square root, which is 121. So that is the square root of 121, which is 11. Also, I'll need to take the derivative of that. Maybe it'd be good if I think of this as x to the 1/2. So the derivative of this is bring the power down and reduce the power by 1. So f prime of 121 is going to be 1 over 2 square root of 121. That ends up being 1/22. So what's my linearization? 11 plus 1/22 times x minus 121. So f of 123 is approximately in linearization at 123, which is 11 plus 1/22 times 123 minus 121. That ends up being 11 and 11 plus 2 22nds, or 11 plus 1/11. Okay, how did that estimate go? Let's take a look. Now, 123, I don't know the square root of that. And what was our guess? 1 plus 1 over 11. Again, pretty good. Good to essentially 3 decimal places. Let's try again. How about the cube root of 123? Well, let's say that this function is going to be our cube root function, which maybe I'll write as x to the 1/3. What value am I going to use for tangency? Well, what's the number near 123 that I know the cube root of? How about 125? So that's the cube root of 125, and I know that to be 5. Let's take the derivative. That'd be 1/3, bring the power down, reduce the power by 1. And let's find the value of that derivative at 125. I get 1 over 3, and this is going to be the cube root of 125 squared. Or maybe I should write it the other way. 1 over 3, and I'll take the cube root first. 125. See if I can write that legibly. That'd be good. 125. Let's take the cube root, and then let's square that. So it's 1 over 3. Cube root of 125 is 5. Square it. That's a 25. So it looks like my slope is 1/75. My linearization then is the y value, 5, plus 1/75 x minus 125. So what is the approximate value of this function at 123? Well, it can be approximated by 5 plus 1/75, 123 minus 125, or 5 minus 2/75. Again, let's see how well we do on that estimate. 123 to the power of 1/3, that'd be our cube root, is 4.97. And what did we say? That was going to be 5 minus, what did we say? 2/75. 2 divided by 75. Again, very, very close without doing tons and tons of work. All right, so there we see it, the value of using linearization. the AP College Board will use the expression linearization. Again, just remember, it's a synonym for tangent line. Now, this next thing is not AP testable, but I think it's really, really cool. And it's called Newton's method. And let me give you an idea of what's going on with Newton's method. Let's say, we've got some function, right? And let's say I want an estimate of where that zero is. I could make a guess as to that zero, and I could draw a tangent line to that point. That tangent line is going to cross the zero, or cross the axis. I can then find where that zero is on the curve and do another tangent line. And if I do this successively, eventually the tangent lines get closer and closer and closer to the real zero, as long as I choose a good first guess. Now let's back this up and talk about where this formula comes from then. Okay, so I'm going to back up. I guess it won't let me back up too much more. Okay, so we start with this. Well, that's too far. Go back here. Forward. So is the drawing going to come back for me? I hope so. There we go. There's our line. There's our initial point. All right, and there's our initial guess. Okay, we're going to call this initial guess its x value. We're going to call it x1. And of course, the tangent line is going to be found by saying the linearization is f of x1, the y value, plus f prime of x1, the slope of that function at that point, times x minus x1. Now remember, we're interested in finding out where that tangent line crosses the axis. So we're going to say, I want to know when is this equal to 0? And I'm going to make the claim that the x value that makes that 0, that's our second guess. That's our x2. Well, let's go ahead and let's try to solve for x2. We'll take f of x sub 1 over the other side. So we get negative f of x sub 1 is equal to f prime x sub 1 times x sub 2 minus x1. Let's divide both sides by f prime. So I get negative f of x sub 1 over f prime x sub 1. And that's equal to x sub 2 minus x sub 1. And then let's add x sub 1 to both sides. So there we have it. X sub 2, our second guess, can be found by taking x sub 1 and subtracting it by f of x sub 1 divided by f prime x sub 1. Now, that will get you x sub 2. If you want x sub 3, you just repeat this process, but you use x sub 2 in all of those different positions. And what we say in general is codified right here. You want to find the next guess, take the previous guess and find that example. All right, let's try this out with actually trying to find a 0 of that particular equation. So let's say f of x is equal to x cubed plus 3x plus 1. All right, and f prime of x is equal to 3x squared plus 3. All right, and where do we think there might be a 0 here? Well, let's take a quick graph of this and see what we can see. I'm going to add a graphing page, and I'll put in x cubed plus 3x plus 1. There's our function. So it looks like There's a zero somewhere between -1 and 0. Let's make 0 our first choice. All right? Now, to make this really work well, I'm going to put the derivative function 3x squared plus 3x squared plus 3. I'm going to put it in F4. Our original function is F3. Our derivative function is in F4. And remember, our formula is guess minus function's value at that guess divided by the derivative value at that guess. All right? So I'm going to add calculator page, and I'm going to say our first guess was 0 minus, and it was f of 3 at 0 divided by, where did we put the derivative? F of 4 of 0. If I do that, why did I get f of 4, 0? Oh, I forgot to put that function in. What was it? Derivative is 3x squared plus 3. Enter. Okay. Now I can go here. Let me try this again. So our first guess was 0. Our second guess using this method is -1/3. When we looked at the graph, did we think it looks like about 1/3? It sure does. That's not a bad guess. Okay, but what can we do? Can we make another guess? Can we take that -1/3 and plop it into our formula? -1/3. In this case, it's going to be minus division F3 at -1/3, and divide this again by F4 at -1/3. And I'm going to do a control enter here, so we don't get a fraction. We'll get an even, we'll get a decimal representation, right? So that's a pretty good guess. I've done this iteration twice. How close is it to the real answer? Well, let's go find out. Menu, analyze graph. Where are those zeros? Where's it? I'm going on this graph in between here. Wow, that's pretty good. -0.322, and we said it was -322. And that was only two iterations, and the calculations for these functions are pretty straightforward. So that's Newton's method, a very, very cool way of finding roots using nothing but derivatives.